So welcome back. Let's continue our discussion of MOS electrostatics by solving the Poisson equation. And we will do this in the depletion region, where it turns out we can make good approximations that allow us to easily and accurately solve the Poisson equation in this region. So let's see how that works. So remember, we understood MOS electrostatics in terms of energy band diagrams. Our reference is flat band. When we apply a negative voltage, mobile holes accumulate. When we apply a positive voltage, if the positive voltage is not bigger than the critical voltage, we deplete the semiconductor. If it's bigger, we also invert. So we are going to focus on solving the MOS electrostatic problem when we are in the depletion region. So let's look at the energy band diagram in depletion region. We will be in depletion when we've applied a positive voltage on the gate, but it's a positive voltage that is such that it doesn't bend the bands too far. And the critical surface potential for that band bending is this quantity 2 psi b, which is determined by how the semiconductor bulk is doped. So you can see from the energy band diagram, from its slope, that there's a positive electric field near the surface. That positive electric field is pushing the holes away and pushing them into the bulk and depleting this region near the surface of mobile carriers. It depletes it approximately to a depth W sub d. There isn't an abrupt edge to this. It's kind of smooth, but we can approximate this by saying we're completely depleted of mobile carriers to a width WD, and after that, the number of mobile carriers is exactly equal to the doping density and everything is neutral. So the electric field only exists in this surface region where we have some charge. Well, we need the space charge density in the Poisson equation. So in general, it depends on mobile holes, mobile electrons, and the ionized dopant density. This is just a p-type semiconductor, so we have p-type dopants. And the depletion approximation that we're making here assumes that as long as we're in this depletion region, the region where Y is less than W sub d, the depth of the depletion region, that the number of holes in that region is negligible compared to the doping density. The number of electrons is also negligible because we haven't bent the conduction band down far enough to invert the semiconductor. So the space charge density is very simple. It's just minus Q times the doping density. We'll assume that all of the dopants are fully ionized. Okay. All right, so we have the space charge density. Outside the depletion region, it's 0. If we have the space charge density, we can solve the Poisson equation and find the electric field. So our Poisson equation in 1D, its divergence D is equal to rho. In 1D, it's D displacement field dy is equal to rho of y. Okay. Well, in the region near the surface where we have an electric field, we can write the displacement field as epsilon times the electric field. Then we get the derivative of the electric field with respect to y is equal to the space charge density over the dielectric constant. The space charge density is just constant, Q times the doping density. So we will see that the slope of the electric field is constant, given by the doping density. The relative dielectric constant is the dielectric constant is the relative dielectric constant of silicon, which is about 11.8 times the permittivity of free space, epsilon naught. All right, let's look at the electric field then. We can see from the energy band diagram that it's positive. If we plot the electric field versus position in this depletion region here, we can see that it has to be a straight line like this. It has to be a straight line because the Poisson equation says that dE dy is minus QE over dielectric constant. So it has a constant slope. It has some value at the surface, we'll call the surface electric field, and it goes to 0 in the bulk because there's no electric field in the bulk. The bands are flat there. So it's easy just to write down this electric field, and we see it's just a straight line. Now we can write a little equation. It has some value at the surface. It goes to 0 at y is equal to WD. So the electric field is given by this expression. Okay, that'll give us our positive electric field in the depletion region. If we put y equals 0, we can solve for the electric field at the surface. This is going to be something that we'll need from time to time. And we can see that it is Q times Na times width of the depletion region divided by dielectric constant. Now, we're going to need to get comfortable. We're going to be seeing equations like this frequently. Q times Na is the space charge density per unit volume. W sub d is the depth of the depletion region. When I multiply the two, I get the charge density per square centimeter. I'll call that Q sub s, the charge in the semiconductor per square centimeter. That's an important quantity that we're going to be looking at over and over again. So the electric field is equal to, actually it's the charge in the depletion region is negative because ionized acceptors are negative. So the electric field is minus the charge in the semiconductor divided by the dielectric constant. Or we can multiply through by dielectric constant epsilon and see that the displacement field at the surface of the semiconductor is just minus the total charge in the semiconductor. That's going to be useful for us to remember. All right, so we have the electric field versus position. That was relatively easy for us to get from the Poisson equation. Now, we remember that the definition of electric field is it's minus the gradient of the electrostatic potential. Okay, that means if I want the electrostatic potential versus position, I just integrate minus the electric field versus position. If I want the total potential drop across this region, that's the surface potential. If I want the total potential drop, then it's just going to be the area under this curve. The area under a triangle is 1/2 height times width. So we have an expression for the surface potential in terms of the surface electric field and the depth of the depletion region. Well, we saw earlier, we have an expression for the electric field. If we put that expression for the electric field in terms of the depletion region depth here, we now have an expression. If we know the surface potential, we know how deep that depletion layer depth is, and we learn that it gets deeper and deeper as the square root of the surface potential increases. All right, so that's a very important result, one that we're going to use frequently. All right, now we can also ask, what is the charge per square centimeter in the semiconductor? Right? That's the charge per unit volume, Q minus Q times Na, times the depth of this depletion region where that charge exists. So we'll call that Q sub d. That's the depletion charge in coulombs per square centimeter. We just multiply minus Q times Na, that's the volume charge density due to the ionized dopants, times the depth of the depletion region, and we get an expression for the charge versus surface potential. So the charge, the magnitude of the charge increases as the square root of the surface potential. That's going to be important. We're going to see these results over and over again. So this is what we call the depletion charge. In general, the semiconductor charge consists of both the depletion charge, and if we bend the bands far enough, there will also be a charge due to the mobile electrons when we create an inversion layer. We're assuming now that we haven't bent the bands that far, so we only have depletion charge to worry about. In this case, the total charge in the semiconductor is very nearly equal to just this depletion charge, and that depletion charge varies as the square root of potential, which I mentioned earlier, so now we see where it comes from. When we qualitatively sketched this charge in the semiconductor versus surface potential, I argued that in the depletion region where the surface potential is positive, but not too positive, that depletion charge in magnitude grows as the square root of the surface potential. And that's exactly what we've derived from this depletion approximation. So we see where that comes from. Let's take an example just so we can get comfortable with how some of these numbers play out. P-type silicon, doped 10 to the 18th per cubic centimeter, room temperature 300 Kelvin. You may recall that Ni in the intrinsic carrier density in silicon is almost exactly 1 times 10 to the 10th. Let me just assume that we've bent the bands by 0.5 volt. the surface potential is a half a volt. KT over Q is 0.026 at room temperature. And I'll need a dielectric constant of silicon. I'll assume it's 11.8. And we're interested in, for these, fairly typical situations, what is the depth of the depletion region so that we can get calibrated on that? And what is the magnitude of the electric field at the surface? How strong is that? Is this a big electric field? Is it a small electric field? Well, before I do this, I should check, because the formulas that we have derived are only valid when we are in depletion. If we have bent the bands to inversion, they're not valid anymore. We bent the bands by a half a volt. We need to be sure that that half a volt isn't enough to create an inversion layer. So basically, we need to assure ourselves that a half a volt is less than 2 psi B. Well, psi B, we have an expression that's just related to the doping density in the bulk. We can put numbers in. Psi B is about a half a volt. So 2 psi B is almost a volt. We only have a half a volt of band bending, so we're comfortably in the depletion region. We can use the formulas that we've derived. Okay, so now that we know that we can use our depletion layer formulas, we take our depletion approximation expression for the depletion depth, W sub D. We simply plug in numbers, and we find out that we get 25.6 times 10 to the minus 9th meters. That's 25.6 nanometers. That isn't very deep. So you're seeing that when we push the mobile holes away from the surface, a little ways away from the surface, it's just a few nanometers deep that we're pushing the mobile carriers away. But that's a typical number. You can kind of see that as you decrease the doping density, if I were to decrease the doping density by a factor of 100 to 10 to the 16th, I would increase the depletion layer depth by a factor of 10. Then that'd be 256 nanometers. So it depends on how the semiconductor is doped. All right, so that's a typical number. What about the electric field? Well, I remember that the electric field, the surface potential was the area under the electric field versus position curve. So we had a simple expression between the surface electric field, the width of the depletion region, and the surface potential. We were given the surface potential. We've computed the depletion layer depth. We can solve this expression for the electric field at the surface, put in numbers, and when we put in numbers, we're going to find that we have, basically, the answer is 390 kilovolts per centimeter. That is a pretty strong electric field. So you can see that even though we've only bent the bands a half a volt, the band bending is occurring over such a small distance that these are very large electric fields that we are talking about. All right, so that's the depletion approximation, how we solve the Poisson equation assuming the depletion approximation, and how we make use of those formulas that we derive in order to compute some quantities that we're going to need over and over again as we move forward in the course. So just to summarize, I've done everything with a p-type semiconductor. We're assuming the situation where we put a positive gate voltage on, deplete the surface, and we have shown how we can compute the electric field versus position, and then very simply compute the depth of this depletion region, the magnitude of the electric field, and the total charge that is now in the semiconductor due to this depleted region. The rest of the semiconductor is neutral. To test your understanding of this, you might redo everything with an N-type semiconductor and see how all of that plays out. All right, the next topic. We've seen how if we know the surface potential, we can compute quantities that we're going to be interested in. Depth of depletion regions, charge in the semiconductor, electric fields at the surface, things like that. Everything depends on the band bending in the semiconductor or the surface potential, which is the same thing. Now, the trouble is, if you go in the lab and put a voltage on the metal gate, you're not directly adjusting the surface potential. You're putting a voltage on the gate, which then indirectly creates some surface potential. So we need to understand, given a surface potential, what gate voltage produced that surface potential, because then we can relate what happens in the laboratory to what actually happens inside the semiconductor. So we'll talk about that gate voltage and surface potential relationship in the next lecture.